Hi, in this video we are going to take a look at the concrete implementation of a very simple neural network. If it would be a complex neural network, we should create a distinct class for the input layer, the hidden layer, and the output layer. We should create a distinct class for the node representing the neurons in our neural network. But here, because we just have very few neurons, we just have a simple neural network class which will handle all our problem. So in our app.java class, we just instantiate a new algorithm. The algorithm is going to, let's go step-by-step basis. So it has an initialize method. It is going to initialize the neural network for us. We have a constant class with a private constructor that prevents us from instantiating this class, and we use this class to contain the static final constant variables that we need, such as the training iteration. We are going to have 1,000 training data. The number of inputs is 3. We have an input neuron for the x coordinate. We will have an input neuron for the y coordinate, and the third neuron will be the bias neuron, as we have discussed. And of course the learning rate is something like this. So this is the initialize. Then we have the function. This is the function that's the separator, the line. It is just the basic constant too, but we can use something like this. For example, here it is a horizontal line at the y equal to 2 point. So here we have a train, and this method is going to iterate through the training iteration. So we are going to make 1,000 iterations, as we have discussed here, and we just simply generate random values in the range 0 to up to 10. It is going to be a double for the x coordinate. For the y coordinate, we will have an answer if it is below the line, and the line is going to be defined by this function. So if it's below this line, the answer is going to be -1. We assign a value that -1 is the case when we are below the line. The +1 denotes that we are above the line. Then we have a temporary input array. It is going to be a double, an array, one-dimensional array for doubles. The 0 is for the x coordinate. The 1 represents another neuron that stores the epsilon coordinate, and the third neuron is the bias neuron, and as we have discussed, it always have value 1. Then we train our neural networks as many times as we have specified in the training iteration static final constant variable, and we just train. Then the predict function is to make a prediction, for example, whether the x is 1, the y is 4. Let's make a prediction with our neural network whether this point is above or below or line. It doesn't have to be a line, it can be a spline, for example, or a quadratic function, a sine wave, whatever. So let's go to the neural network. Here we have a random field variable to randomly initialize the weights for our neural networks. We have store references to the weights, and of course the learning rate. So in the neural network, here, as you can see, when training the neural network, when we instantiate the neural network, we specify the number of inputs and a constant learning rate. So here we just initialize the class accordingly with the new random. We initialize the weights. So we iterate through the weights, the number of weights, and initialize it randomly, and then set the learning rate to the learning rate we have specified here. Then, as we train our algorithm here 1,000 times, we call the train method. And this train method is going to have a guess according to this feed-forward method. We call it feed-forward in neural networks usually. It just sums up as we have discussed. We have to sum up the given node's value times the weights of that given edge pointing to the given node, and we have to sum these up. And then we have to decide according to the activation function whether we use a sigmoid function, no, not a sigmoid function, but a signum function. If it's greater than 0, it's going to be +1. Anyways, it's going to be -1. This is the signum function. We could use the sigmoid function or the hyperbolic function to be more precise, but in that situation we would need the derivatives, and we should use partial derivatives, which is not so hard because the derivative of the hyperbolic function are given. We can calculate it without any problem. So here we are going to calculate the sum. We calculate the activation value. It is +1 or -1, and we just return with that value. And this is going to be the guess, and with the help of this we are going to calculate the error. For example, I make it double, but whatever. If the desired, it is the value we have calculated here. We know that the answer is going to be -1 or +1 because we know it for sure from the training data, and here according to this function. So here we have the desired function, which is the right answer. I think in the theoretical section I call it like this. And we calculate the error in a simple algorithm. We just right answer minus the guess. And this is how we adjust the weights, if you remember. It is the same as I write weight I plus the learning rate times the error times the inputs I. The order is not quite right because we use it something like this. Inputs I. Weights. Okay. So we keep adjusting our edges accordingly. This is how the train method is working in a neural network. And then after training our algorithm, we can have a prediction. We want to predict whether the 1 and the 4, what value it's going to give us. It is above the line, so the given point is above the line. It's working fine. It's returned a 2. It is a horizontal line, and the intersection with the y-axis is 2. This is how described. I'm not sure whether we are familiar with this basic math or not, but it's working fine. If I use something, I want to predict that whether the x is equal to 2, the y is equal to 1, it is going to be below the line. So it is below the line. It is a very trivial situation, so we do not need any neural networks to be able to predict it. But it just for demonstration purposes, I think it's a very good example to see how these neural networks works in practice. And it's good because it's very simple. We do not have to use. We could use for the activation function the sigmoid function. We should use derivatives. We should use for calculating the error terms. For example, the square mean errors, a bit more difficult. Use, for example, gradient descent to be able to find an optimal solution. But in this situation, with the help of this very easy activation function, we can do it and calculate it very easily. And I think it's a very good in order to grasp the fundamentals of neural networks. And anyways, if you want to use more complex neural networks, you should definitely use MATLAB or R, for example. Both of these software contains these kinds of techniques, because otherwise it was very, very hard to implement neural networks on your own. So this is how we implement a basic, very, very simple neural network. Thanks for watching.